In this video, we're going to talk about joint discrete random variables. Now, this part should be review from Stat 230. When we get to joint continuous random variables, that will be new, but everything in this video should be review. First of all, we can define the joint CDF of a bunch of discrete random variables as big F of x1 through xk. And that's just the probability that each of those variables is less than or equal to each of those values. And it's defined for all real k-tuples x1 through xk. The properties are basically it's got to be between 0 and 1 no matter what, and it's also going to be non-decreasing in each of those arguments xi. If we want to know more specifically about each variable, the joint probability function of a bunch of discrete random variables x1 through xk is what we call p of x1 through xk. And that's the probability that each variable is equal to each of those values, little xi. And it's defined for all k-tuples x1 through xk that are actually in the joint range of those random variables. Not for all real x's, but for all values in the range. We might be interested in extracting information about just one of those random variables from the joint information. And we can do that if we essentially sum over all of the unwanted variables that we don't care about. So if we do that, we'll obtain the marginal probability functions. Formally, if x and y are discrete random variables with a joint probability function pxy, then we say the marginal probability function of x is p sub x of x, and we get that by summing pxy over all y. And we can do the same thing in the opposite direction. The marginal pf of y is p sub y of y, which we get by summing over all x. We could extend that to multiple variables if we like. Let's look at an example. Suppose x and y have the following joint probability function. I'm going to give it as a table. X can take values 1, 2, and 3. Y can take values 1 and 2. And the joint probability function is given in the table, 0.1, 0.2, 0.3, 0.2, 0.1, and 0.1. Now, we could imagine anything we want for these random variables, but I want you to think about this. Imagine x and y are the number of products from two competing brands that purchasers have acquired. Given that they have at least one from each of the brands. So maybe X could be Apple and Y could be Microsoft, and this is the probability that an individual owns this many products from each of those two competitors. You'd be interested in maybe doing some market research on the competition between those companies. All right, what we want to do is find the joint CDF as well as the marginal PFs of each of those two variables. For the marginal probability functions, we can just sum down the columns to get px of x and sum across the rows to get p sub y of y. And that gives us our marginal probability functions. For the joint CDF, we can actually just add up the values. So the probability that x is less than or equal to 1 and y is less than or equal to 1, the only possible value is when x and y are both equal to 1, and that has probability 0.1. But if we want these two values here, x less than or equal to 2 and y less than or equal to 1, or the opposite, y less than or equal to 2 and x less than or equal to 1, we add up the probabilities 0.1 plus 0.2. And we can fill in the rest of the values as follows. Notice that, first of all, when we look at the value in the bottom right corner, that's the maximum of x and the maximum of y, that gives us 1. And as well, the bottom row and the rightmost column give us the individual CDFs of the variables. Now we can talk about independence. We say that discrete random variables x and y are independent if and only if the probability function for the two random variables together, that joint probability function, is equal to the product of the marginal probability functions for all xy in the joint range. Let's look at this example. Can we determine whether they're independent? Well, p of 1, 1 is 0.1, but px of 1 and py of 1 are not equal. So in this case, x and y are not independent. And that makes sense if they're the number of products purchased by competing brands. There's a few quick ways we can check for dependence, actually. Any single pair xy that doesn't satisfy this property is enough to prove that variables are dependent. But we could also just consider the range. If the joint range of the random variables is not a rectangle, in other words, more technically, it's not a Cartesian product of the sets, then we know the variables are dependent in some way. So imagine we had x and y, and the squiggly lines are just non-zero numbers, but we have a 0 over there. The range there is not a rectangle. It's like a a trapezoid, I guess, which means that the values depend on the other values, which means that we have dependence. But be careful, the converse is not true. We could have a lovely perfect rectangular range, but still have dependence. In fact, the example we just did had that. Next, I want to talk about the multinomial random variables. It's a collection of variables defined as follows. Imagine we have a series of independent trials, and we're going to do n of them, similar to Bernoulli trials, but not quite the same thing, because the possible outcomes are not just success and failure. We have outcome 1 with probability p1, etc., down to outcome k with probability pk. And those pi's are constant and sum up to 1. So we're going to let xi be the number of outcomes of type I that we get in those n trials for I equals 1 up through k. So we have k random variables, and we say that their joint distribution is a multinomial with parameters n and p1 through pk. Let's see if we can find the range and the joint probability function of this collection of multinomial random variables. For the range, we can obviously see that each xi has to be between 0 and n, because we can't have more than n outcomes or less than 0, but we also need the sum of the variables to be exactly n. So the joint range is going to be all k-tuples, x1 through xk, that satisfy this, that are non-negative and sum to n. Now that's clearly fewer possible values of these x1 through xk's than all possible combinations. So that means we don't have a Cartesian product of sets, and we can immediately tell that these variables, x1 through xk, are not independent. Think about that for a second. It seems a little bit weird. We've said that the trials are independent, but the variables are not. Now think about, if we knew that one variable was very close to n, that means a lot of the outcomes were one particular type. Of course, that tells us something about how many outcomes there could be of all the other types. So even though the trials are independent, the variables are not. Okay, for the probability function, we want the probability that we get x1 type 1s, x2 type 2s, etc. up to xk type k's. And that is just the probability of p1 to the x1 through pk to the xk. That would be the probability of getting those outcomes. But they could be ordered in a number of different ways. They could be ordered in n factorial ways, but we also have, we can't tell the difference between the type 1s, between the type 2s, etc., and between the type k's. So the number of ways to arrange those outcomes is actually n factorial divided by x1 factorial, x2 factorial, etc., up to xk factorial. If you've forgotten that, no worries, that was a pretty obscure result from Stat 230. Those are known as the multinomial coefficients. So this together gives us our joint probability function for these k variables. But actually, since we know that the variables sum up to n, we could express xk as n minus the other xi's and just simplify to having k minus 1 arguments. And that's sometimes useful to do that. We'll play around a lot with the multinomial distribution actually in the tutorial coming up on Wednesday. So you'll have lots of chances to work and play around with this distribution. Next, I want to talk about expectation in the joint case. We might be interested in knowing the mean or variance of some function of x and y. You can probably think of lots of cases of why that might be useful to us. If we have two random variables, we might want to know the mean or variance of a linear combination or even a nonlinear combination. Like if x and y, for example, are the returns on two stocks, then the value of a portfolio would be a function of those two returns. And we'd be interested in knowing more information about that function of x and y. So we can define the expected value or expectation of some function g of xy as follows. It's just e of gxy, and it's the double sum over all x and all y of g of xy times p of xy. So again, it's like a weighted average of the g of xy values where the weights are pxy. Now, if g of xy happens to be a linear function, we end up getting a really nice result that I'm actually going to prove for you here. If we want some linear combination ax plus by, by definition, that's the double sum of ax plus by times the joint probability function pxy. Well, we can split this sum up into two sums with ax on one side and by on the other side. And then we can pull a outside and pull the x outside the sum over y, and similarly pull b outside and pull y outside the sum over all x. But That probability there, pxy summed up over all y and summed up over all x, those are just by definition the marginal probability functions of x and y respectively. So then we get a times the sum over all x of x p of x and b times the sum over all y of y p of y. Well, those are just the expected values. And so altogether we get a e of x plus b e of y. In other words, we've just shown that expectation is a linear operator. It preserves linear transformations. But be careful. In general, e of g of xy is not equal to g evaluated at those means. It only works if g is a linear function of x and y. If x and y happen to be independent, we get another nice result. If we have e of g of x times h of y, we can split that up into the product of those two functions. And I want you to try to prove this one. It's really, really easy to do. Just sub in the definition of the expected value of this function, and then use the fact that with independence, p of xy can be factored into px of x times py of y. Give that proof a try. See if you can do it. All right. We might also be interested in the relationship between variables. Whether or not they're independent is one thing, but we might want to quantify the relationship if it exists. And for that, we define the covariance. The covariance is cov xy, and it's just the expected value of x minus ex times y minus ey, but way more commonly and way more usefully, we can calculate it as e of xy minus e of x times e of y. We can interpret the covariance in a couple of different ways. If the covariance is positive, that means x and y tend to move together in the same directions. X is large when y is large. If it's negative, x and y tend to move in opposite directions. So x is large when y is small, and vice versa. And if the covariance is 0, all that tells us is that x and y have no linear relationship. And I want to emphasize that word linear. It doesn't mean they have no relationship at all, just no linear one. If x and y do happen to be independent, then e of xy is just equal to e of x times e of y by that result before. So the covariance will be 0. But the converse is not true. Independence implies 0 covariance, but 0 covariance does not imply independence. They could just have a nonlinear relationship. Here's an example. If x is binomial with parameters 10 and 0.5, and y is x minus 5 squared, you can show that the covariance is 0, but clearly they're not independent. They're definitely very closely related to each other. One is literally a function of the other one, but their covariance will be 0. Here's a thought question. If the covariance is non-zero, what can you say about the relationship between the variables? Give that some thought. All right. The covariance itself is great, but it can't really be interpreted in terms of the magnitude. So we also define the correlation between x and y as the covariance divided by the square roots of the variance. And we sometimes give that the Greek letter rho. That's not a p, it's a rho. In terms of the interpretation, the sign has the same interpretation as covariance. If it's positive, they move together. If it's negative, they move apart. And if it's 0, they have no linear relationship. But rho is bounded between -1 and 1. So we can also interpret the magnitude as a measure of the strength of the linear relationship. If it's really close to plus or minus 1, we have a strong relationship. But correlation, even a strong one, does not necessarily imply causation. That's a common misconception. All right, let's look back at the example from the beginning of class. I want to find the correlation between x and y. I want you to follow along and see if you can calculate all of these quantities on your own. We're going to need e of x, e of y, e of x squared, e of y squared, and e of xy. If you can get those 5 things, try it now. You should be able to follow along with the calculations. I'm not going to show all the details, but I'll give you the final results. So if you have any trouble with that, practice until you can get it. So e of x you should find is 2.1, and e of y is 1.4, and e of xy gives us 2.8. So with those 3 things combined, we can find that the covariance is actually negative 0.14. Then we have e of x squared is 5.1, which tells us that the variance of x is 0.69. E of y squared is 2.2, which tells us that the variance of y is 0.24. And all that together tells us that the correlation of x and y is negative 0.344. And that's looking like a sort of medium to weakish negative relationship between those quantities, x and y. And again, if X and Y are the number of products purchased by one person from two competing brands, it should make sense that there would be a negative relationship between them. All right, lastly, I want to talk about one more useful thing about covariance, and that's looking at variance of linear combinations. If we want the variance of ax plus by, that is a squared times the variance of x plus b squared times the variance of y plus 2ab times the covariance of x and y. You could show this by using the definition of variance and just manipulating within the brackets. So we'll end up with the covariance playing a role in the variance of linear combinations. And that's really helpful. Remember, if x and y were, say, two stock values, the relationship between them, whether those stocks are positively or negatively correlated, would have an impact on the overall variability and riskiness of the portfolio of those stocks. If they're super highly correlated together, have a large covariance, then the risk is going to go up because both your stocks will do well or poorly at the same time. But if you find stocks that are negatively correlated, that's going to reduce the risk of your portfolio. We can actually generalize this. If we want variance of any linear combination of variables, say the sum of ai xi, we can write that as the sum of ai squared times the variances plus 2 times the sum where I is less than j of ai aj times the covariance of xi xj. We're not going to be using this too much, so if this is a struggle for you, don't worry about it. Often our coefficients are all just 1, so then that makes that easy, but this is what we can do if we want the variance of a linear combination. And similarly, just for completeness, we also know that the expected value of the sum of ai xi is the sum of ai times the expected values. We know that because that's just applying the rule of expectation being a linear operator. So that is everything for this video. In the next video, we'll look at almost all of these ideas again, but see what happens when we turn to joint continuous random variables. Instead of our sums, we'll have integrals and we'll have some derivatives going on, and everything will be a little bit weirder, but basically everything works the same way in the continuous case. And we'll see that in the next video.